Pluto's way will undoubtedly cause issues from the very start. Pluto's circle meets that of another planet. Pluto, the secretive and humble planet situated in the farthest corners of our planetary group, has turned into a hotly debated issue in cosmology. Late updates recommend a possible crash with Neptune, raising cautions among researchers and space lovers. Eminent figures, for example, Neil deGrasse Tyson and Michio Kaku, have expressed concerns regarding the potential consequences of this divine experience. Yet how did Pluto end up on a crash course with Neptune, and what could this cosmic conflict mean for Earth? Join us as we investigate the subtleties of how a monstrous event with Neptune could have happened, and why researchers are disturbed by this enormous irregularity. Pluto, once celebrated as an undeniable planet, went through an emotional renaming as a dwarf planet, largely due to its whimsical circle. Despite this downgrade, Pluto continues to captivate and ignite interest within the galactic community. Late warnings from prominent researchers, such as Neil deGrasse Tyson and Michio Kaku, have suggested that Pluto's way could cross that of Neptune, inferring a potential risk of a crash with serious ramifications for our planet. Pluto's journey around the Sun is remarkable because of its extraordinary qualities. Its circle is especially lengthy, requiring a huge 248 years to complete. Since its discovery in 1930, Pluto has not yet completed a full revolution around the Sun. What makes Pluto even more captivating is the supercurved state of its circle, a glaring contrast to the almost roundabout circles of the major planets. Furthermore, Pluto's circle is tilted at an angle of 17 degrees relative to the ecliptic plane, resulting in a more extreme slope compared to the orbits of other planets. This combination of tilt and its elongated circle adds complexity to its movement. A fascinating part of Pluto's circle is its repeated convergence with Neptune's orbit. Every 248 years, Pluto's path brings it closer to the Sun than Neptune, which challenges what we would expect from their general positions in the solar system. Further investigation reveals that Pluto's circle is far from an ideal circle. Rather, it follows a circular or oval path, meaning that its distance from the Sun fluctuates significantly throughout its orbit. At its closest point, Pluto comes within about 30 astronomical units of the Sun, but at its farthest, it stretches to over 49 astronomical units, almost twice the distance of Neptune from the Sun. In addition, Pluto's orbit is tilted at an angle to the orbits of other planets, adding yet another layer of complexity to its relationship with Neptune. This inclination plays a crucial role in how Pluto and Neptune interact. When their orbits intersect, their gravitational forces pull at one another, gradually altering their paths. This dynamic between Pluto and Neptune highlights the interconnected nature of the solar system, with each planet exerting gravitational forces that influence the movements of others. Over the years, technological advancements in observational instruments have allowed astronomers to track Pluto's movement with greater accuracy. This has led to a better understanding of its orbit and its potential effect on the overall stability of the outer solar system. Although the likelihood of a direct collision between Pluto and Neptune remains low, the possibility is still under scrutiny. Ongoing monitoring continues, as the potential consequences of such an impact could be dramatic. Despite Pluto's small size and its distant location, it remains a subject of interest for researchers and space enthusiasts alike. A key question that arises is, why hasn't Pluto crashed into Neptune by now? The answer lies in the gravitational influence of other planets. From the moment Pluto was discovered, space experts have been trying to understand its orbit. Unlike most planets, which maintain a stable orbit along the ecliptic plane, Pluto's orbit stands out with its steep angle and eccentric shape. The mystery deepened when it became clear that Pluto's orbit crosses Neptune's. Despite this apparent danger, Pluto's orbit remains surprisingly stable, demonstrating the intricate mechanics that govern space. Studying the interactions between Pluto, Neptune, and the Sun presents a significant challenge for astronomers. Predicting their movements involves a deep understanding of how their gravitational forces affect each other's paths. To tackle this challenge, researchers rely on models such as ASMU libration, scope libration, and VSOP, as well as the theories of Steves and Kaplan, to solve this cosmic puzzle. SMU libration, for instance, is crucial in maintaining the stability of planetary orbits. When Pluto crosses Neptune's path, it stays at least 90 degrees away, preventing a direct collision. Scope libration ensures that when Pluto approaches Neptune or other large planets, it is positioned above their orbit, reducing the likelihood of a crash. The VSOP model, named after researchers von Zeipel, Steves, and Kaplan, explains why Pluto's orbit appears irregular but remains stable over time. Although space seems turbulent, there are fundamental patterns that help keep everything in order. These patterns are responsible for preventing Pluto from slamming into Neptune or significantly altering its orbit. The concept of orbital chaos, which describes how a celestial body's path is highly sensitive to its initial position, is clearly demonstrated by Pluto's orbit. Even small variations in Pluto's position or velocity can lead to significant changes over long periods. Researchers use advanced computational models to simulate Pluto's interactions with other bodies in space, like Neptune, and to investigate the outcomes of even minor shifts in its orbit. In the late 1980s, these simulations revealed something intriguing. Despite the apparent stability of Pluto's orbit, it can still behave erratically. A tiny adjustment in Pluto's initial position or speed could lead to massive changes in its orbit over time. However, even with these uncertainties, Pluto's orbit remains stable for billions of years, suggesting that despite its unpredictable appearance, it follows an underlying order. The unpredictability of planetary orbits, such as Pluto's, makes it difficult to predict long-term changes with certainty. These models require highly precise initial conditions, as even small blunders in information can deliver immeasurably various outcomes, making exact expectations extraordinarily testing. Understanding Pluto's circle is fundamental, especially while considering the potential for a future crash with Neptune. This information adds to a more extensive comprehension of how our planetary group works. Pluto's circle serves as an illustration of how apparently turbulent ways can at last arrive at an equilibrium. Directed by the forces of gravity and movement, we must proceed to notice and concentrate on these divine mechanics to acquire a superior comprehension of our position in the universe. Pluto's circle offers an ideal delineation of the flighty nature of space. Pluto's circle is not like that of other planets, with its oval shape leading to capricious interactions with Neptune. This sporadic movement makes it hard to foresee the long-term dynamics of the system. However, gravitational forces play a critical role in holding Pluto and Neptune apart. Gravity, a force that draws objects to each other, ensures that, despite their converging orbits, the two bodies remain separated most of the time. These interactions reflect the sensitive balance of forces at work in space. The chance of an impact between Pluto and Neptune, while implausible, would be a grand event with huge results. Such an event would undoubtedly alter how we understand the local planetary group. However, space exploration has progressed significantly. Pluto's circle serves as a reminder of the many questions that still exist. Scientists continue to study Pluto's path to better understand how large planets affect its motion. This information is crucial for understanding the complex relationships between celestial bodies and how their movements can impact one another. Despite the surprising nature of Pluto's orbit, some of the world's leading scientists, like Neil deGrasse Tyson, have speculated that Pluto might one day crash into Neptune. Tyson, a prominent astrophysicist, views Pluto's reclassification as a dwarf planet as a crucial step, recognizing the importance of continued investigation and study. He believes that Pluto's peculiar orbit underscores the fact that there is still much to discover about space and the forces at work within it. According to Tyson, the mysteries of space are what makes studying it so captivating, and he encourages others to engage with the fascinating intricacies of divine mechanics. Tyson, along with other specialists, is concerned about the potential risks posed by Pluto's strange orbit. If a crash between Pluto and Neptune were to happen, it could have devastating consequences for our planetary system. The release of energy from such an event would be colossal, and the debris scattered throughout space could have sweeping impacts, potentially even affecting other planets and moons. Neptune itself would be impacted, and its orbit could be altered, further complicating the dynamics of the outer solar system. Renowned theoretical physicist Michio Kaku, known for his work in string theory, also offers valuable insights into space exploration. Kaku believes that studying phenomena like Pluto's orbit is essential for understanding the broader principles of celestial mechanics and theoretical physics. He suggests that examining Pluto's interactions with Neptune can help scientists navigate future space missions more safely. Kaku also emphasizes the importance of understanding gravitational forces in space exploration, as they have the potential to shape the future of how we explore distant worlds. Kaku's work in string theory, which seeks to explain the fundamental forces of the universe, aligns with his interest in Pluto's orbit. A collision between Pluto and Neptune could provide valuable data that would enhance our understanding of gravity and spacetime. Key to string theory: although such an event would directly impact Earth, it could offer a unique opportunity to study the behavior of fundamental forces in extreme conditions. As scientists continue to explore the depths of space, the unpredictability of planetary interactions becomes more apparent. The study of celestial mechanics, such as the unpredictable gravitational relationship between Pluto and Neptune, provides valuable insights into the fundamental laws of the universe. By continuing to monitor and study these phenomena, we draw closer to understanding the vast and complex nature of the universe. The gravitational dance between Pluto and Neptune demonstrates how even distant planets can influence one another. These celestial bodies exert gravitational forces that, over extended periods, can shape their orbits in subtle yet significant ways. While a direct impact remains unlikely, the possibility cannot be completely ruled out, leading to continued interest and observation from the astronomical community. Scientists believe that understanding these forces may one day allow them to predict and potentially mitigate the risks posed by such celestial events. One fascinating aspect of planetary movement is how seemingly irregular or tumultuous interactions can lead to stable, predictable patterns. This phenomenon is especially evident in the case of Pluto, whose orbit might appear erratic but is actually governed by precise gravitational forces. These forces help keep Pluto from crashing into Neptune, despite the apparent overlap in their paths. The delicate balance between the gravitational pull of other planets and Pluto's orbit keeps the dwarf planet on a steady, albeit complex, course. Understanding this intricate relationship is crucial for advancing our knowledge of the broader solar system. As scientists continue to study the unique characteristics of Pluto's orbit, they also look toward other areas of space exploration. The study of systems like the TRAPPIST-1 system, which contains several Earth-sized planets, helps astronomers understand how gravitational forces between planets can lead to orbital resonances and, in some cases, increase the likelihood of a planet's orbit becoming unstable. However, the TRAPPIST-1 system is not currently experiencing any such effects. Researchers remain cautious, monitoring the movements of planets in these crowded conditions to better understand the risks and how they might evolve over time. In the meantime, astronomers are also focused on understanding the behavior of rogue planets, which wander through space without being bound to a star.